Hello, you are welcome. All right, so having studied linear motion in one dimension, which of course is rectilinear motion, so we are going to extend it right to motion, linear motion in two dimension. Okay, so one of the um, common application of linear motion in two dimension is uh, projectile. So we are going to be studying projectile in this particular video. What is a projectile? Okay, so from this diagram you can see the motion of a projectile. The motion of a projectile is a motion that actually follows an angular path from the point of projection, right? So invariably, if you are describing the motion of a projectile, we are not looking at vertical upward movement or vertical projection of the object. We are not also looking at just the horizontal movement, of course, but we are looking at the motion of an object in which the velocity is actually the velocity is released. The initial velocity is actually released in an angular path. So such motion is known as projectile, right? So this is angular, the motion of an object in an angular path from the point of projection to the point it actually comes back to the ground level. All right. So at this point, the object actually reaches the maximum height. This is maximum height. Okay. So from the point of projection, it reaches the maximum height. Then from the maximum height, it follows the same parabolic path then to the ground level. All right. So the distance from the point of projection to the point, all right, the horizontal distance from the point of projection to the point it returns back to the ground is known as the range. R is the range. All right, R represents the range. While the initial velocity is inclined at an angle theta, so this angle theta is referred to as the angle of projection, angle of projection of the projectile. All right. So, as a matter of fact, I'm very sure that you can actually, all right, you can give an example, right, of a projectile. So one good example of a projectile is javelin. Okay, please follow me. Okay, one good example of a projectile is javelin. Okay, so please pardon me. Let me fix in what I need. Okay. All right. Okay, so let's begin. Okay, as I was saying, one example of a projectile is a javelin. Example of projectile is javelin. All right. So you throw a javelin. Then we now have in technology we have missiles that is actually released from a particular camp to the enemy's camp. This is actually a missile is a weapon of war. Okay, so that's just by the way. Okay, so let's now look at how we are gonna solve questions on projectile. What equation do we use? Do we still use the equation of motion? Yes, we will need to use the equation of motion, but before we actually apply the equation of motion, we should actually consider the fact that the velocity this time around, the initial velocity, okay, that this projectile actually is being released with is in two dimensions. Why is it in two dimensions? Because the velocity is neither vertical. Let me draw that. Okay, so the velocity is neither vertical nor horizontal. So this is, let's say this is the vertical component of velocity. Let me call it uy. And this is the horizontal component of the velocity. But the velocity of a projectile the projectile we are talking about is neither vertical nor horizontal, but rather it is inclined at an angle. Okay, and always take note of this. Anytime you physics a particular vector quantity, which of course this time around you're looking at the velocity, is actually inclined at an angle. All right. In this case, this vector quantity, the initial velocity, is inclined at an angle. We can actually resolve it into two components: the vertical component and the horizontal component. So, the vertical component, if I should actually draw a line from this velocity horizontally, okay, to, let me draw this line, okay. So this is the vertical component of the velocity. Let me call it, of course, it's uy, and of course, this is the horizontal component ux. And from what you see, from what we have actually constructed right here, we have a right angle triangle. So both the vertical component and horizontal component, and of course the velocity itself, form a right angle triangle in which uy is the opposite. This is the opposite of the right angle triangle. The ux is the hypotenuse of the right angle triangle. Okay. The us is the adjacent, please pardon me. The adjacent of the right angle triangle. Adjacent. While the velocity itself is actually is the hypotenuse. Okay. So now we are resolving this velocity into two components, the vertical component and the horizontal component. Let's start with the vertical component of the velocity. Vertical component. All right, the vertical component of the initial velocity. Can we begin? Yes, we can. All right, so the vertical component of the initial velocity is uy, which of course is the opposite of this right angle triangle, while the velocity itself, u, being the hypotenuse. So we're going to find a ratio that corresponds to opposite and hypotenuse. Don't forget the ratios, okay? That is abbreviated as SOHCAHTOA. So invariably, opposite all over hypotenuse is sine. So the sine of theta is equal to the opposite, which of course is the vertical component that we're looking for, divided by the hypotenuse, which of course is the velocity u. So for us to now find the vertical component uy, all right, we'll cross multiply. If I cross multiply, I'll now have that the vertical component of the initial velocity, okay, because u is the initial velocity. In some textbook, okay, some textbook you're going to see something like v naught of y. Okay, so they use v0 to represent in, the initial velocity. But since already I'm using u, okay, so u would do. So I'm looking at u, y to be, the, of course, being the vertical component. If I cross multiply, that's going to give me u sine theta. So the vertical component. So anytime I'm considering the velocity of a projectile, in the vertical direction, okay, all I just need to do is to multiply the velocity u by sine theta. That will give me the vertical component. Please take note of that, and we can also do that for the horizontal component. All right. So for the horizontal component, this time around we are looking at adjacent being the horizontal, and of course hypotenuse, that is cos theta from our trigonometrical ratio. Cos theta is equal to adjacent, that is the horizontal component, divided by the hypotenuse, which is u. So I will still have to do the same if I cross multiply. So u of x being the horizontal component is u cos theta. So anytime I'm considering the velocity in the horizontal direction, is going to be u cos theta. So please take note of that. So invariably, if I'm using my equation of motion, all right, depending on what I'm looking at, I can either use the vertical component of velocity or the horizontal component. So what are those parameters that we actually consider in projectile? Okay, The very first parameter we consider in projectile is what is known as the time of flight. Okay, but before the time of flight, we need to find the time. First of all, the time to reach the maximum height. So we use small letter t for this, as we already know. So going back to my projectile, as you can see, the motion of this projectile is divided into two halves. One half, okay, please pardon me. One half of the motion, okay, one half of the motion, the object actually moves from the point of projection then to the maximum height, all the way from the point of projection to this point to the maximum height. Then from the maximum height, it will return back to the ground. So the time it takes to reach the maximum height, okay, is small letter t. It will take the same time to move from the maximum height to return to the ground level, another small letter t. So the total time of flight, which of course is capital letter T, is going to be equal to t plus t, which of course is 2t. All right, but first of all, let's evaluate the time it takes the projectile to reach the maximum height. So small letter t. So we're looking at, let's write down the parameters. We're looking at small letter t, okay? And don't forget that we still make use of the acceleration due to gravity, which of course is g. All right, we make use of g, which is of course is approximately, of course, 10 meter per second square. But we are not going to use it. We're just going to use the symbol because we want to derive the formula for the time to reach the maximum height. Then the question is, what component of velocity are we going to consider if you're looking at maximum height? The component of velocity, initial velocity, we are going to consider is the vertical component. Okay, so the velocity we are looking at is the vertical component, uy, which of course is u sine theta. Okay, then finally, for this object at maximum height, don't forget it's an object moving under the influence of gravitational force. At maximum height, the final velocity is equal to 0. So now, which equation of motion will help us find the time to reach the maximum height? That should be the very first equation of motion. Okay, so equation of motion under gravity, that is v is equal to u. Okay, in this case that's uy, then minus gt. All right, so putting the values, v is 0, uy we know already is u sine theta, then minus gt. So rearranging the equation, I'm going to move minus gt to the right side. That's going to give me gt is equal to u sine theta. So with what I have now, t is going to be equal to u sine theta, then of course divided by g. T is equal to u sine theta, then divided by g. I hope that is well understood. All right. So having, please pardon me, having gotten this, now this is the time it takes that object to reach the maximum height. Then the next parameter is we need to actually derive is the time of flight. Okay, so which we already know is capital letter T, time of flight. So we know that the time of flight is always 2 times the time to reach the maximum height. That is 2 small letter t. So small letter t is u sine theta all over g. So that's going to be the time of flight is going to be 2u sine theta all over g. So that is the derivation for the time of flight of a projectile. So please take note of that. Another parameter we need to derive is actually the maximum height. We need to know the expression for the maximum height attained by a projectile. And the symbol, let's use capital letter H. All right, so let's write parameters. So the maximum height, of course, is the height, of course, vertical distance covered. All right, let's look at that. So the parameters we'll still know is we're going to use the fact we're going to use v at maximum height to be equal to 0. The u we're going to consider is still going to be the vertical component of u sine theta. Then the g still is a parameter. All right, and finally the maximum height, capital letter H, question mark. So which equation of motion carries everything here? That is the second equation, which of course is H is equal to ut minus half. Okay, so the u we are looking at here is not just u, is the vertical component of u. So that's going to be u of y t, then minus half gt square. Okay, does no, that is not the equation because I have v. So the equation that will go, the ideal equation is the third equation, which of course is v square is equal to u square then minus 2gh. Of course, that's u of y square minus 2gh. Okay, so of course this is 0 square. U of y is u sine theta. Then it is, we square it all square minus 2gh. So if we rearrange this equation, minus 2gh comes to the other side, that's going to be plus 2gh. U square, u is being squared, that is u square. Then sine theta is squared, that is sine square theta. So to make h now the subject. Okay, so let me just use small letter h. We are familiar with small letter h, okay? So let it just be small letter h. So in this case, small letter h is going to be equal to u square sine square theta, then divided by 2g. So this right here is the expression for the maximum height that is attained by the projectile. Then the last but not the least parameter that we need is the range of the projectile. We talked about the range by the symbol R. The range is the horizontal distance, okay? So of course, this is the projectile. So from this point to the point where it returns to the ground is the range. So what parameters are we looking at? This time around, the velocity we are looking at is going to be equal to the horizontal component of the velocity. So because that is horizontal distance, range is horizontal distance. So we are going to be looking at the horizontal component, which of course is u cos theta. But in the horizontal direction, gravity, all right? In horizontal direction, gravity is equal to 0. Don't forget, gravity is equal to 0. And since gravity is equal to 0, the time, already the time we need the time, because at this point, the object has actually covered its motion. So the time we need is the time of, the total time of light, which we already know it is 2u sine theta all over g. So what are we looking for now? We're looking for the horizontal distance, which of course is the range. So which equation of motion captures all this? Range here, okay, becomes is the same as x or h. So that is the second equation. Second equation, we know that distance, okay, yes, I'm not mistaken. So the range being the distance, okay, which of course is equivalent to the distance or even the height, is equal to u of x multiplied by the time, which of course is the time of light, then minus half gt square. Half gt square. Now, the whole of this term is equal to 0. The whole of this term is equal to 0. Why? Because g is already equal to 0. So 0 multiplied by everything here is 0. So we're only left with the range is going to be equal to u of x, which of course is u cos theta. Then multiply by t, which of here is times 2u sine theta all over g. All right. Of course, in advanced mathematics, when you do advanced trigonometry, okay, you should be familiar. All right. If you have done advanced trigonometry, you should be familiar with this trigonometrical identity 2u 2 sine theta, okay, cos theta. 2 sine theta cos theta, 2 sine theta cos theta is always sine 2 theta. U times u is u square. So that simply means that the expression for range is going to be u square, then multiplied by 2 sine theta cos theta, which of course is sine 2 theta. Some 2 theta all over g. So that is the last but not the least. So this is the final expression for the range, or the final expression for a projectile, the range. Okay, so please take note of this expression. So even if you cannot derive the formula, this formula, okay, getting to remember this formula anytime you need them is really very important, because that is what you're going to use to solve question in as much as projectile is concerned. Okay, so we're going to apply this formula in our next video, and we're going to be solving question on projectile. So see you in the next video. Thank you very much. Hello, you